Hey, 13 Calc. Welcome to the first of hopefully many enjoyable tutorials on differentiation. Problem 1 is on related rates. Now this is getting into related rates is one of the topics that you're very likely to see when you get towards the merit and excellence end of your external. So these would be, I think, more often merit, but occasionally excellence. So let's have a look at this problem. A large spherical helium balloon is being inflated at a constant rate of 4,800 cubic centimeters per second. At what rate is the radius of the balloon increasing when the volume of the balloon is 288,000 pi cubic centimeters? All right, well, let's sort out what we have here. We've got 4,800 cubic centimeters per second. That's how fast it's inflating. So, in other words, that's a change in the volume with respect to time, or dv dt. Now, at what rate is the radius increasing? So we would call that dr dt, and that's what they're looking for here. So the first thing you want to do is write an equation which solves for the unknown that you want. In this case, dr dt, the rate of change of the radius over time. So we're going to write dr dt equals, well, the only thing I have in here so far is dv dt, so I'll put that in. And then I got to think about, well, what can I multiply this by in order to get the ratio that I want? And think of this as a ratio. So if I've got dt where I want it in the denominator, but I've got a dv instead of a dr in the numerator. So I've got to cancel that dv out by putting it down here. And then what I want in this numerator here is dr. So if I take the rate of change of the volume and multiply by the rate of change of the radius with respect to volume, then I'll have my answer. So how do we relate these two features of the sphere, volume and radius? Well, it's through this formula here. Volume equals 4/3 pi r cubed. And this is really the key to solving this. So I've just got a v on the left, and all I've got is r on the right. So I can just go ahead and differentiate this v in terms of r. So we would call that dv dr equals, and this is just the power rule. So I'm going to take my power and multiply by the coefficient. So it's 3 times 4 pi over 3. That's going to give me 4 pi. And then I'm going to reduce the power by 1. So my derivative there is 4 pi r squared. So hopefully by now you've noticed, well, that's not what I wanted. I need dr dv. And that's where this idea of looking at these as ratios comes in handy. So if dv dr is 4 pi r squared, then I can say dr dv is just the reciprocal of that, right? 1 over 4 pi r squared. And now I've got a formula, a general formula for this derivative. I can say dr dt equals, and well, dv dt I know is 4,800, and then dr dv is 1 over 4 pi r squared. So I'll just put that in the denominator here, 4 pi r squared. So I'm almost there. I just have this this radius at this instant when I know the volume. So here I got to use this again, right? So I've got 288,000 pi. That's my volume at this instant. And that's just 4/3 pi times the radius at that instant cubed. So I can go ahead and solve this. I got some pi's canceling. So I've got r cubed equals, I'll go over to the calculator and do 288,000 times 3 divided by 4, and that's going to give me 216,000. 216,000, and then, well, I can just take the cube root of both sides here. So I'm just going to shift cube root that answer, and I got 60. So my radius at that moment is 60 centimeters. And now I can plug that back into my formula for r. So I've got dr dt equals 4,800 over 4 pi times 60 squared. And let's head to the calculator again. 4,800, and I'm dividing by 4 and by pi and by 60 squared. And that gives me 0.106. 0.106. Now it's a radius which is increasing, so that's going to be increasing in centimeters per second. And that's my answer to this one, 0.106 centimeters per second. Okay, I hope this helps. See you next time. Bye-bye.